sorry, can you see my screen?
Yes, you can.
Okay. Great. Okay, perfect. Great. And you can hear me? Is that right? Yeah. All right.
Yeah,
great.
No problems.
All right. Great. Well, thank you so much to the organizers for organizing this very stimulating workshop and for giving me the opportunity to speak. So today I'm going to be discussing hybrid Fracton orders. So this is about a recent work that was done in collaboration with Nat Tantivasadakarn at Harvard as a graduate student there, and also Wenjie Ji, who's a postdoc at UCSB. And this will be part one of two talks. This one will be about the work that's already on the archive, and the second part right afterwards, which is by Nat, will be about some generalizations of what I'll be presenting here. Okay, so to give a very brief kind of background for the kind of key differences between topological orders and Fracton orders that I want to focus on in this talk, and which will be important when addressing hybrid Fracton orders. So in 3+1D topological orders, so generally the deconfined phase of a G gauge theory where G is a finite group, there are mobile excitations, which are deconfined charge excitations of the gauge theory. These are point-like excitations that are free to move in space. And along with these, there are these loop excitations, which are flux loops. And there's often some universal data in these gauge theories, not only the fusion of the charges and the fluxes, but the mutual statistical phase accumulated, for example, when a charge goes around a flux. So in a Z2 gauge theory, for example, this is a phase factor of pi when a Z2 charge moves around a flux. And along with this, there's three loop rating and other universal data that can be extracted from these gauge theories. And in contrast, gap Fracton orders are very different in that they're immobile or point-like excitations with highly reduced mobility. And there are, broadly speaking, two kinds of Fracton orders that I want to focus on and that have been identified in the literature. One kind is exemplified by the so-called X-cube model. So this is a model of a Fracton order in which the point-like excitations come in a kind of a hierarchy of increasing mobility. So the point-like excitations could be Fracton-like. Multiples of them can move along lines, and multiplets of those can move along planes. But there's no topologically non-trivial quasi-particle that's free to move everywhere. And another formal definition of these kinds of type 1, so to speak, Fracton orders comes from their foliation structure. That is, in the X-cube model and in similar models which have a hierarchy of quasi-particle excitations like this, one can act with a finite depth local quantum circuit to exfoliate two-dimensional topological orders. This is in contrast to a quantum liquid, and in that case, really one is allowed to add trivial product states, not highly entangled states of a lower dimension. So this is a type 1 order, and an example of a type 2 order, which is even more dramatically different, is Haas code, in which all of the point-like excitations are immobile. And in fact, in this case, the point-like excitations suffer from a logarithmically growing energy barrier that one has to overcome in order to separate them out by distance, which makes this kind of code useful from the standpoint of quantum information storage. So the dramatically different properties of these two kinds of orders motivates maybe an interesting question, which is whether there are three-dimensional orders which actually combine the phenomenology of both conventional topological orders and Fracton orders in a non-trivial way. And the message of this talk is that there are these hybrid Fracton orders, which are gap phases of matter with excitations that have a very strict correspondence with excitations that you would find in either a Fracton order or a topological order in 3 dimensions. Nevertheless, these hybrid orders are inextricable in the sense that one can't peel off the 3-dimensional topological order from the Fracton order, because these two species of excitations have non-trivial fusion and braiding amongst each other. In addition to that, these hybrid Fracton orders can be thought of as parent states for a pure Fracton order and a conventional 3+1D topological order, in the sense that they contain the order parameters for both kinds of phases, and in the sense that one can condense an appropriate set of gapped excitations in these hybrid orders in order to realize either kind of order. So the focus of this talk is specifically going to be about hybrid orders, which hybridize, so to speak, a type 1 or a type 2 Fracton order, like the X-cube model or Haas code, with specifically a Z2 topological order. These kinds of hybrid orders admit two complementary perspectives. And in this talk, I'll be taking one of them and presenting it in some detail. The other perspective, which is to view a hybrid Fracton order as the deconfined phase of a gauge theory in and of itself, will be presented in Nat's talk. So yeah, in this talk, I'm going to primarily focus on one key example, which I'll call a one-foliated hybrid order. So this one-foliated hybrid order, you should think of as hybridizing, so to speak, or blending the phenomenology of just a stack of Z4, a stack of Z2 toric codes rather, and a 3D Z2 topological order. So the construction of this hybrid order is as follows. We can start with just a stack of 2+1D Z4 toric codes. So there are gapped flux and charge excitations in each layer of the Z4 toric codes. They're initially decoupled, and the excitations are labeled as shown on the screen. The charges are E squared, E cubed, and the notation is to exemplify their fusion rules. So E and E cubed fuse to the vacuum, and E squared fuses with itself to the vacuum, and the fluxes are labeled similarly M squared, and M cubed. And importantly, these two species of excitations have a braiding phase of e to the I theta, where theta is given by the expression on the screen. So initially, these layers are decoupled, but by condensing an appropriate set of excitations across the layers, we can realize a phase which is kind of hybridizing a Z2 topological order in 3 dimensions with a stack of 2D toric codes, Z2 toric codes. Specifically, what we can do is we can consider condensing pairs of the E squared charge across adjacent layers in this stack of 2+1D Z4 toric codes. So this couples the layers together in some non-trivial way. And we can ask what the properties of the resulting phase are if the condensate now consists of this fluctuating configurations of these E squared charges, which have been condensed across adjacent layers. So because of the non-trivial braiding phase that E squared has with some of the other fluxes, this will naturally confine some of the excitations, but we'll find in the resulting phase that there's a kind of hybridized phenomenology. So specifically, if we were to schematically think, so one could write down a lattice model that does exactly this, but to think schematically about the properties of the resulting phase, we only have to think about how the condensate braids with the original excitations in the stack of toric codes. So we can first think about the charge excitations. So if I condense E squared across adjacent layers, then the individual E squared charge, which was previously confined to a single layer, can now move between the layers because of the condensate. And in addition, the single Z4 charge within a layer had no statistical phase with E squared. So this E Z4 charge is now confined to strictly move within a layer, but remains a deconfined excitation of the resulting phase. So of the original charges, we now have an E planon. So this E excitation is restricted to move within a plane, and we have an E squared mobile charge, which can move everywhere. And importantly, the original fusion rules of the Z4 toric codes implies that if I take 2 of these planons and fuse them together, so 2 of these E's, I actually get E squared, which is an excitation, which is a mobile charge, which is free to move everywhere. So in contrast, the fluxes are a bit subtle. So for the fluxes, the M and M cubed fluxes braid non-trivially with the condensate, and they become confined. However, if I think about forming an excitation which is loop-like, that is, I string together a bunch of Z4 fluxes across the layers in a loop, as shown on the screen in blue, then this excitation actually braids trivially with the condensate. So this kind of flux loop becomes a new kind of excitation in this phase. And in addition, the M squared excitation in each layer braids trivially with E squared. And now I have another kind of conjugate planon that now lives in each layer as well. So to summarize, the fluxes, the M and M cubed become confined, but I now have a new flux loop that lives across all the layers, and M squared, which is a planon, which is restricted to live within a plane. So this is there's, in addition to this, these excitations kind of inherit the statistical phases that one already has present in the Z4 toric codes. So the E squared mobile charge braids with this M flux loop, and moving one around the other yields a minus sign, which is this statistical phase of pi. So, right. So in addition to this, the planon can also move around the flux loop. And in this case, consistency with the fact that two planons fuse into a mobile charge actually gives a different statistical phase, a phase factor of I, when the planon moves around this flux loop. So to summarize, this is a phase in which I have a mobile charge and a flux loop along with two different conjugate species of planons. And the mobile charge and the flux loop have fusion rules and mutual braiding phases that are reminiscent of a Z2 topological order in 3D, whereas the planons are similar to the Z2 charges that one would find in a single toric code layer Z2 toric code. So it's actually possible to generalize this to hybridize the 3D Z2 topological order with other Fracton orders such as the X cube order or Haas code. And the quasi-particle content in the resulting hybrid order takes the following very general form. So I can label the excitations of the Z2 topological order as E squared for the mobile charge and M for the flux loop. And in the Fracton order I want to hybridize this with, I'll label one of the excitations in the Fracton order, say, I'll call it an E particle. This could be a Fracton, a linon, a planon, etc. And a conjugate excitation of the Fracton order I'll label as M squared. So as a very concrete example, in the X cube order, there's a Fracton and a conjugate linon, excitation. And I can label one as E and the other as M squared. The hybridized order, which is an entirely new kind of order, has a generating set for which label all the possible excitations, which are as follows: 1E, E squared, M, and M squared. And these are suggestive. These are in correspondence with the labelings here. So E, E squared, M, and M squared are respectively mobile charges, loops, fractons, or linons. And the labeling is suggestive of their fusion rules. So what I originally labeled as a Fracton, say E, in the Fracton order, fuses, if I take a pair of them, into a mobile charge, which behaves like the charge in the Z2 topological order. Similarly, a flux loop will actually fuse into some collection of immobile excitations of the Fracton order. So this is general for this setup where I'm hybridizing the 3D Z2 topological order with the X cube order, Haas code, or other kinds of let's say one-foliated Fracton orders. In addition to this, there are non-trivial statistical phases, one of which I'll point out here, which is that the flux loop, which behaves like the flux loop in the Z2 topological phase, has a non-trivial braiding phase with the Fracton, which is inherited from this kind of this other Fracton order. So for example, anytime we hybridize the Z2 topological order with the X cube order or Haas code, the flux loop is able to remotely detect the Fracton of the X cube or Haas code with this statistical phase factor of I. Okay. In addition to this, there are many other kind of fusion and braiding processes that we can think about. So for example, we can actually choose to hybridize the X cube model with the Z2 topological order in actually two different ways. So in the labeling of this generating set, I can actually choose E to either be the Fracton excitation of the X cube model or the linon excitation of the X cube model. And that yields two different kinds of orders where the fusion rules and the braiding are very different. So in one case, if I choose E to be the Fracton of the X cube order, then fusing two of these together actually gives a mobile Z2 charge, which behaves like the Z2 charge of the 3D Z2 topological order. And in that so-called fractonic hybrid X cube order, the conjugate excitation, M squared, becomes a linon. And the loop excitation of this hybrid order is such that the loops actually fuse into excitations into linons, which are like the linons of the X cube order. So specifically in this hybrid order, if I take two loop excitations and fuse them together, then I'll find that there are linons at the corners of the loops. And the fact that the corners of the loops carry some energy cost after doing some fusion of the M loops also implies something else, which is that a pair of the Fracton excitations in this fractonic hybrid X cube order can actually remotely detect a corner of one of these M loop excitations. So specifically a pair of these fractons which form a planon, as they would in the X cube order, detect this corner because if I take a pair of these M loops, I should be able to find that there's a line on at this corner. And consistency with the braiding phases one would get in the X cube model imply this kind of remote detection process.
Sagar, you're just about out of time. You can take another minute or two.
Okay, great. I'll wrap up in just a minute. To complete this setup, we can also have what ainonic hybrid X cube order, where we can choose the particle which I labeled as E in the hybrid X cube order to be the line-on of the X cube model. And in that case, fusing two of the line-ons together gives me some topological excitation, which is similar to the mobile charge in the Z2 topological phase. And we can also hybridize Haas code with the 3D Z2 topological order. And in this case, the loop excitations of the resulting hybrid order fuse into a very intricate pattern of Fracton excitations which surround the loop. And this depends on the detailed geometry of the loop. So I'll just conclude by saying that these hybrid orders can be thought of as parent states for Fracton and conventional topological orders in a precise sense, in that the hybrid orders have both order parameters, both non-local order parameters, and in that if I condense either M squared or Z or E squared, we can obtain different kinds of orders, pure Fracton order or pure 3D topological order. So one of the examples is shown on the screen, but I can address more questions about this or discuss this more detail during the discussion section. So here's our summary, and thanks.
All right, thank you very much for an excellent talk, Sagar. All right, and our last speaker for this session will be